I'd like to introduce you to my longtime collaborator, Dr. Rick Baldwin in chemistry. He does have a Ph.D. from Purdue. Don't let that fool you. He is a true and true Cardinal fan, probably one of the bigger that I know here. He has been on the faculty here for 41 years teaching chemistry classes, and I know he probably taught some of you your, what class, the 100 or one of the first early level chemistry classes, since if you're in bioengineering, you have to take that. And he's also served as the editor of a distinguished journal, Analytica Chemica Acta, since 2000. So he's here to talk about some of our research.
Those are clearly my students from earlier.
Yes, right.
Project I'm going to talk about we've been engaged in for 6 or 7 years now, from the time the idea first occurred to us. And I'm going to start kind of oddly by acknowledging the contributors to the project at the beginning, because I tend to forget things doing that at the end. And it's important to this project. So this is a joint project between several of us, myself and some students in chemistry, and also a couple of illustrious bioengineering faculty. The chemists involved are Mohammed Mareh, who received his Ph.D. under my direction a few years ago, did the initial part, probably most of the work I'm going to talk about, and my current student, Kelsey Kott, who is doing the more recent things. I'm a chemist, so I'm going to talk mostly about the chemistry involved. You can ask about the engineering. I don't know as much about the details of that as Tommy or Dr. Kenton would, but I'm going to focus mostly on the chemistry because that's what I do. Okay. It's a problem I want to talk about. And actually, I started working here in 1976. This problem actually, aspects of it date back to 1976. Many of you have probably heard of something called Superfund. Well, in the old days, the 60s, we weren't very environmentally conscious. And it was in 1970s that some of the famous pollution incidents, the Love Canal, for example, occurred. That caused a lot of legislation in order to regulate and chemical waste and the storage of waste. And that's referred to as the Superfund. And it's still in existence. These sites here they're now 1,342 Superfund sites. These are waste storage sites that are somehow being monitored or supervised. That number goes up over time. It's not going down. They do potentially clean up some of these sites, but the cleanup is a lot slower than the identification. Sites are scattered throughout the U.S., generally near where there is industrialization. A famous, you see Louisville, Kentucky here, one of those sites, there's a famous Superfund site in Bullitt County near Jefferson Forest called the Valley of the Drums. That was an old farm where the guy who owned the farm made money by just accepting drums of various unidentified chemicals. There were at one time 100,000 drums just sitting out in this field rusting away. That site has been officially cleaned up, although whether that's been taken off the list, although I don't know whether that cleanup has been effective or not. So we have lots of waste storage sites that are just sitting there. Well, what's in them? What do we have to worry about? Well, the EPA has compiled a list of toxic or hazardous substances. This is its top 10. That's based on toxicity, the quantity of material that's out there, its transport in the environment, and so forth. And you can see some very nice guys are sitting at the top of the list. Arsenic, lead, mercury, cadmium. Those are all heavy metals. That's what I'll be talking about. There are other pollutants, organic pollutants out there, but I'm going to be interested mostly in heavy metals. And those are some of the bad guys. This is a nice view of a bunch of guys kayaking, having fun on a river. What's wrong with this picture? Well, rivers aren't usually that color. This is the Animas River in Colorado. In August 2015, out west there are a lot of gold mines, abandoned gold mines, that have lots, when you mine gold, you get lots of heavy metal waste. And in a lot of cases, this heavy metal waste is just sitting there in sludge ponds. In August of 2015, the EPA was plugging a site which was leaking something like 100 gallons a minute. Unfortunately, they unplugged the site and they released 3 million gallons of wastewater that contained 500,000 kilograms of heavy metals, and that's what happens to the color of the river initially. This was one mine, and there are estimated to be 500,000 similar mines out there. So there's waste storage, there's also this official like the Superfund. This was not a Superfund site. But then there's just places like this where they're storing waste. Flint, Michigan, we've all heard of that. That's lead in drinking water. This particular heavy metal I want to talk about most of the data today is arsenic. It was at the top of the list. Now arsenic has been known to be a problem for decades. Started out in Southeast Asia where the deep wells over there, which were drilled in order to improve the quality of the drinking water, simply added a lot of arsenic to the drinking water that the mostly poor people in Bangladesh, Cambodia, and other places in Southeast Asia drink. Long-term exposure to arsenic causes lots of problems, including cancer. Problem is not restricted to Southeast Asia. A few years ago, China did a survey of its wells. It uncovered, it has 500,000 wells were sampled, and 5% of them contain more than 50 ppb of arsenic. The EPA World Health Organization limit for arsenic in drinking water is 10 ppb. So it's a big problem. If you think, well, we're the US, we've got clean water here. Well, this is the arsenic in surface soils in the US. Louisville is right here, and it's one of these red spots. Now, I'm not saying that our arsenic in your drinking water is a problem. I think Louisville Water Company is a good, reputable water company. But arsenic is all over the place. Let's go back to this guy. So this was an emergency site that was in the news for a long time. It was targeted. And after about a year of study, the Colorado Health Department issued the following recommendations. Well, very quickly, relatively quickly, the yellow color disappears. These are heavy metals, so they're largely insoluble. So the color goes away. But the metals are simply going to the bottom of the river. They're not going away. So in order to monitor this, the big plan here was that they would choose 4 sites on hundreds of miles of river where they would take weekly water samples. It's like 15 times a year. They sample it more times during the rainy season when the water's flowing. So they're only looking at 4 sites on an occasional basis. They haven't chosen 3 sites where they installed permanent monitors, but these monitors are that they use here only measure physical parameters like pH, temperature, conductivity. They don't make real chemical analyses. So even for a well-known site like this, the amount of monitoring is, maybe it's the best we can do. That's the state of the art, I guess. But it certainly doesn't seem to be something I'd be comfortable with if I were drinking this water. So what are we going to do about it? Well, how do we monitor things now? Well, that was an example. We have 2 approaches now. You can send a guy out to the river and he'll collect a sample, or she'll collect a sample and bring it back to the lab. The central labs are great places. They have all kinds of fancy equipment. They can do wonderful analyses of heavy metals. Problem is, you've got to choose a few times to send the guy out to get the sample. And so you only get a snapshot analysis. If things were okay when you collected your sample, that's fine. But if things weren't okay the day before, that's not so fine. So this paradigm that is most in effect now involves sample collection, taking it back to a central lab. Now, what you get out of that is a high-quality analysis. You've got expensive, sophisticated equipment. You can have people who know how to run that equipment, and you can do all kinds of sample treatment to get the sample ready for analysis. So there's nothing wrong with that, except that it only provides you a snapshot. Another approach is to use portable instruments. There are a lot of instruments that we can make small and you can haul out to the site. Perhaps that's a little bit better, but it still only provides a snapshot because you've got to be out there with a technician at a particular time and place. So both of these strategies provide only limited information, and they're generally pretty expensive because you have expensive equipment, you have to pay a guy. So they're near the real time, they're certainly not continuous, and the number of sites that you're looking at is very limited. So, what's the solution? Well, we want a real-time, continuous 24/7 type of monitoring system. And we have to emphasize that portable is not what we're after. We're looking to have an instrument that's on site all the time that can give us analysis either continuously or at least on demand. So what we're envisioning is, I suppose the water company wants to monitor its drinking lines. There are 4,000 miles of water mains in Louisville, most of which are being torn up and replaced right now. But the amount of water that they have to look at is truly enormous. But the system we would propose is to have a bunch of water monitors or sensors that are distributed through the system. And then the people back at the water company headquarters can communicate with these monitors or sensors whenever they want. Now, what I'm going to talk about mainly is the water monitor, the sensor. That's where the chemistry is. The rest of this stuff, the communication, the control, the data collection, all that, we refer to that in my lab as just engineering. I don't mean that. All we're saying is somebody else's job. But the other thing is, unless you have a really good monitor, all the engineering in the world isn't going to do any good. So, what we're envisioning is to create a monitor that you could create a sensing network around a waste site or in a drinking water system. Now, if you're going to do that, and those sensors are sitting out there all the time. So, that's not an easy thing to do. First of all, one of the problems is that when you have a sample in a lab, there's a lot of stuff that you can do with it. But if you have it in the field, you have to worry about powering the sensor. You have to worry about the wireless communication to and from the sensor, the control of the instrument. If you bring a sample back to the lab, you have all kinds of possibilities, like you could treat the sample to make it ideal for your measurement. Doing all of that in the field would be a real burden. Have all that aside, you still need a really good sensor to start with. And what does a good sensor have to be? Well, you want it to have adequate sensitivity to detect what you're looking for. You want it to be cheap, relatively cheap, because you're envisioning a network of dozens or maybe hundreds of these sensors. It's got to be fairly simple, so you don't want to have to treat the sample a heck of a lot out there. It should got to be able to sit on the sidewalk or in a field, summer, winter. But the main thing, the first thing, is that it's got to be able to operate without me or a technician sitting next to it. It's got to be operator-free, and we refer to that as calibration-free. I would challenge you guys to tell me a chemical measurement that is truly calibration-free. The most prevalent, the most important sensor, chemical sensor in the world, does anybody know what that is? A pH meter. pH meters are in every lab around the world. pH is measured millions of times each day. pH electrode is cheap, it works, it's reliable, but if you've ever operated a pH meter, the first thing you do in the morning is calibrate it. It's not calibration free. So what is? Well, if you guys have a suggestion, I'd be happy to hear about it. We might have another research project. But the approach that we came up with is one that's going to either put you to sleep or scare you, because you haven't heard about this since your general chemistry course. Remember electrochemistry? We mentioned it, we threatened you with it, but we never really explained it. Well, I'm an electrochemist, and the approach that we're going to use is an electrochemical approach. Not a new approach. The father of electrochemistry is that guy, Michael Faraday. He lived in the 19th century. What we exposed you to in Gen Chem is probably Faraday's Law. It's that equation right there. Now, this isn't new. Faraday came up with his law in 1834. But what Faraday's law says is if you electrolyze something, that means, I'm going to assume you guys don't know, remember, or haven't retained any electrochemistry. So if you have questions, stop me. I can answer electrochemistry questions, but I'm going to gloss over a lot of stuff just to get the simple ideas through. Well, what you do is you stick an electrode in your sample, you apply a potential that causes the sample to get oxidized or reduced. Therefore, a current flows at the electrode. When a current flows over time, if you integrate that signal, you get charge. So Faraday said that if you carry out such an experiment, you electrolyze a solution, the amount of charge that you measure is given by this very simple equation. N, small n, is the number of electrons involved in the oxidation reduction process. It's a 1 electron oxidation or 2 electron reduction. F is Faraday's constant. That just converts charge to the number of moles. That's 96,485. Generally, we'll know N and we'll know F. N, capital N, that's the number of moles of substance that you're oxidizing and reducing. Very simple equation. Think about a slightly different way to write Faraday's law. Well, the number of moles, that's the concentration, the molarity, times the volume. So this is just another form of Faraday's law. But this tells us that N and F, we know those are constants for any given experiment. Q is what you're going to measure by applying the potential and measuring the current. So that just leaves C and V. Concentration is what I'm interested in. Is the arsenic concentration 10 ppb or higher? So what about V? Well, that's the volume. So our concept is that if you create a cell of fixed volume, so you know the volume, then you electrolyze it completely. So you oxidize or reduce everything in that sample, and you measure the resulting charge. Then you can calculate C. It's the only thing left. This is a technique, coulometry, but in particular exhaustive coulometry, where you oxidize and reduce 100% of your sample, is calibration free. It's independent of temperature and independent of electrode area. There's no calibration standards that you need. So this is the general approach that we're going to be exploring. It's a coulometry approach. Well, now how do we do this? Let's go from 1834 to 2017. This is a drawing of what our electrolysis cell looks like. The sample goes, the electrode is down here in the bottom. That's what it looks like there. That fits in right here. The cell is defined by a piece of material here that we machine out. That's our cell. We do have a 3-electrode system, so there's the working electrode is down here. That's the important electrode. That's the one I'll talk about. In the other compartment, there are the other electrodes, because you have to have more than one electrode to get a complete circuit and all that. So this is our approach. So we're going to flow the sample into that compartment, fill it up. We know that volume. We apply a potential to our electrode down here and allow that electrode to oxidize or reduce that entire sample compartment. While we're doing that, we measure the current and convert that to a charge. What are some of the key elements of this? Well, first of all, that cell's not very big. When we make them, they're usually a few microliters in size. Why do we want them so small? Well, if you're going to put this in the field and you ever have to treat your sample, you don't have to add a lot of acid or a lot of base or a lot of some reagent. So you want to have small samples so you can have the possibility of doing real sample treatment in the field. Also, that sample, the height of that cell, is usually about 100 to a few hundred microns. So it's a thin layer cell. Why do we want it to be thin layer? Well, after we fill it up and we apply a potential, electrochemistry only happens at the electrode surface, at the electrode solution interface. So a molecule that's way out here in solution doesn't get oxidized and reduced. It has to diffuse to the electrode surface. The thicker that cell is, the longer the diffusion time is, so the longer it'll take us to oxidize that entire sample cell. With 100 micron thickness for most species and most common diffusion coefficients, that means you can deplete that cell in less than a minute. So we're aiming, we can make the cells thicker, that'll just make the experiment take longer. It's okay with me, but yeah, I'm old, so I don't have that much time. My students are young, but they don't seem to want to spend that much time. So that's basically our measure. That's our electrode. The electrodes we do manufacture over in the microfabrication facility here. The electrodes can be, usually the ones I'll talk about are planar disc. I'm going to talk today about gold electrodes, that's what works best for arsenic. But you can easily microfabricate all kinds of fancy electrodes. Most of the work is done with a simple single planar electrode. Later on, if I have time, I'm already smelling pizza. I'll talk about a planar electrode that has a network of, it's an array of holes. But that's our electrode system. In action, this is sort of assembled what it looks like. The sample comes in here, goes on our electrode, our working electrode chamber is down here, flows in here and out there. In our work, with the work that Kelsey's doing, she's injecting the sample just with a syringe, so it's manual. That obviously wouldn't work in the field. Okay, one of our first studies, we tried to choose an ideal system. The ideal electrochemical system is ferrocyanide. That's a guy that just gains an electron, goes to this species, nothing chemically of interest happens. It's chemically and electrochemically reversible. You can go back and forth all you want. So we filled our cell with ferrocyanide. We applied a positive potential to cause it to oxidize, caused this reaction to occur. We got a current pulse. These are in units of seconds, so it took about, we waited 100 seconds or 2 minutes, and you see the current initially is fast, is high, then it decays away. Once you completely oxidize the cell, you can apply a reducing potential and reverse the reaction. That's what's happening here. Now we're getting this reaction to go. And since this is stable and it's completely chemically reversible, you can oxidize, reduce, and it doesn't change. That was a good thing. We can do an experiment like that and use that to calculate what the volume of the cell is. So this cell is about 4 microliters. Is this good electrolysis? Would Michael Faraday like it? Well, if we do this experiment for different ferrocyanide solutions containing different ferrocyanide concentrations, and we just plot the charge that's accumulating over time, this goes out to a minute. The blank doesn't give us much of anything, but as we increase the ferrocyanide concentration, the charge that we accumulate builds up. It's a nice linear relationship. So far, so good. So, with our beaming from our success with ferrocyanide, we decided to move not right to arsenic, but to something a little closer. We went to copper. Copper ions, and copper ions can be reduced to copper metal. So we decided to try the system out on something that's not so toxic. This shows results here. This is the current time curve. So we're going to fill our cell up with the copper ions. We're going to apply a potential to cause its reduction. And here we're looking at the current as a function of time. So we apply the potential, start the reduction here. The current spikes and then decreases over time. You can't begin to read that, but that's out at 1 or 2 minutes. You can see the current decreases and goes to the background. These different lines are different copper concentrations. The lower copper concentrations are down here, so the signal that we're getting increases with concentration. That's good. Funny thing about copper, though, is that it's not like ferrocyanide. Both When we do ferrocyanide, both of those species are soluble, ferro and ferrocyanide. But with metals, it's a little different. When you, copper is in solution, copper ions, but when you reduce it, it forms copper metal. Copper metal plates out on the electrode surface. So it's a reversible process, but so we call the two stages there deposition. That's when the copper is going from ions and plating out on the electrode surface. That's the reduction step. When we carry out the oxidation, we're converting the copper to copper ions, so we're stripping the copper off the electrode surface. When we look at the stripping signal, also the signal that we're getting here increases with copper concentration. That's fine. But one thing you cannot possibly see from where you're sitting is the time scale here. This time scale is in a minute or two. This time scale is in less than a second. The stripping occurs much faster. Well, why is that? Well, it's not a mass transfer related process. All the copper metal is sitting on the electrode. All we have to do is apply potential, and it gets oxidized essentially instantly. So when you're dealing with a metal, you've got this deposition stripping issue that you have to understand. If we look at that stripping signal really closely, now you can see the time scale. This is 100 milliseconds here. The blue trace is what we get when we put a blank solution that has no copper in it. You still get some current. That current, there's current that whenever you jump the potential, the electrode has to charge up to the new potential value. That's called charging current. That's very fast normally, and that's what the blue trace is. If we then do the same experiment, add some copper to the solution, and we reduce it, we deposit it, then we strip it off, we get this signal here, the red one. This is a fairly high copper concentration, but you can see that signal is back to the background within 100 milliseconds or so. So the stripping step is very, very fast. Well, turns out that's a good thing. If we prepare a calibration curve where we're plotting for different copper concentrations, we're plotting the charge we get. This is the calibration curve you get if you use the deposition charge. It's nice and linear, it's okay. If you do the same thing but use the stripping charge, which is occurring much faster, you get a linear calibration puzzle. They both have the same slope. They should, because the charge that you're getting from oxidation reduction should be identical. So they should have the same slope, and it does. But this is much more high quality data for the stripping step. You see the uncertainties in the charges we're measuring for the deposition. Well, why is that? Well, the deposition takes a minute. And during most of that minute, the signal is very, very small. So that's low quality data most of the time. The signal to noise ratio sucks for this stuff. But here, we're only integrating for less than a second. And that's all, so there's much less noise that's being built into the signal. So it turns out that the fact that we, with heavy metals, you can deposit them and strip them off helps the measurement a heck of a lot. So every data I'm going to talk about now, in order to get it, is going to be stripping data. In order to get that data, we have to first deposit the metal, but I'm not going to worry about that very much. So if we go back to this guy, so our signal is going to be the stripping signal. And the actual signal here, the blue one is background. The red one is the background plus our signal. So the real signal is simply the area between those two curves. That's the charge that's related to the oxidation reduction of the copper. And so we refer to this as a crescent. So our signals are always the area of this crescent. All right, now, the actual measurement step sequence that we use is a little bit more complicated. Ideally, in the field, we would like to do an in situ background correction. Now, the previous data, to get that blue line, the graduate student running the experiment had to fill the cell up with a blank solution, get the blue line, then fill the solution, the cell up with the analyte solution, and get the red line. 2 steps, you got a lot of pumping and movement going on. You don't want to have to do that in the field. You want to do that background correction in situ. So what we do, what Mohammed Mareh developed, is a technique called double potential step stripping. And what he does is has 4 pulses. First, we apply a reducing potential that's very, very short. Now, at that potential, the copper or the metal could get deposited, but that only lasts less than a second. So only a very small fraction, less than 1% of our copper actually gets deposited. Then we step the potential back to do a stripping experiment, but there hasn't been any much metal deposited, so that stripping is the background. There's no copper involved here. Then we do a third pulse where we step out to reducing potential, the deposition potential again, but now we sit out there for a minute or two. So now we actually exhaust the cell and plate out all the copper or arsenic. Then we step back to do the stripping, and now the stripping signal contains the charge for the oxidation of the copper or arsenic. So it's the difference between this line and this line that really creates the crescent that we're interested in. This is important because this simplifies the experiment out in the field. We don't have to do as much pumping as we might have thought. So let's get to arsenic. Another electrochemical technique I'm going to show you is this is called cyclic voltammetry. What we do is we start at the potential, we scan the potential out negatively. When we get negative, something gets reduced. If we have just take a blank solution and scan at a gold electrode or from this potential region, we get this one wave, this red wave. That corresponds to the reduction of oxygen. Unless you remove it, oxygen is always present in solutions. But I don't see any, but if we do the same experiment and we put arsenic in the solution, we get the gray trace. Now, it still has the oxygen reduction. It's a little different height because it's impossible to control the oxygen content in your sample very well. But you don't see any arsenic reduction. It's buried by that oxygen wave. If we take all the oxygen out of the solution, we deaerate the solution ahead of time, we get rid of the oxygen, and now you can see a little, if you have an imagination, you can see a little wave out there that corresponds to the arsenic reduction. Arsenic's not very concentrated in this solution. And if you go back, you can see a little oxidation corresponding to the stripping of the arsenic. If we blow that up, there's the arsenic reduction. Now, when I say arsenic, I'm talking about arsenic 3. There are lots of forms of arsenic. Arsenic 3 is probably the worst guy. It's certainly the easiest guy to work with electrochemically. So here, arsenic 3 is being reduced to arsenic metal, plating out of the electrode. Here, that arsenic is being stripped off. So we apply our deposition step by stepping out to this, about minus 500 millivolts. We strip it by stepping back to about plus 300. But it's the same deal as copper, more or less. When we do that with different concentrations of arsenic, we get these crescents. That A is for when that's for the blank, there's no arsenic present. As we go on out here, we're going from 100 ppb arsenic to about 1 ppm arsenic. You can see the signal, which is the crescent, is increasing as we go out. That's a good thing. If we go to a table and turn that all into numbers, these are the different concentrations. Now, if you go back, if you would go back, I'll show this slide again. For the blank, that signal had a little bit of a crescent there. The signal wasn't 0 for the blank. It was, in fact, 1.5 microcoulombs. But as you increase the arsenic concentration, the charge increases. That's good. The size of the crescent was getting bigger. But what we have to do is correct the 100 ppb charge for the background. And so the signal due to arsenic is the difference between those two charges. And so if we simply correct this or adjust it by subtracting out that background, we get those charges which are due to the arsenic. Very reproducible. 10% is good for me. It's not good if I'm doing the experiment in the lab, but if it's out on the sidewalk somewhere, 10% is pretty darn good. But we were only down to about 100 ppb. We want to get down to 10 ppb for drinking water. We probably could have, with that system, could have gone down to maybe 50 ppb, but we still want to go lower. Well, what's the problem there? Well, limit of detection, that's what LOD stands for. Limit of detection you want to be as low as possible. That's the lowest concentration you can adequately detect. So limit of detection is determined by the signal-to-noise ratio. The more signal you have, the better the detection limit is. The less noise you have, the better the detection limit is. Well, let's consider our case. Well, there's an old, long-standing analytical technique called ASV, or anodic stripping voltammetry. When you deposit a metal by reducing, then you strip it off by oxidizing it. That's called anodic stripping. That's what we're doing. The traditional way of doing that is to apply that potential for a long time. So you deposit for a long time. And while you're depositing, you can flow, sample, or stir your solution. So in anodic stripping voltammetry, you get down to very low concentration levels because you can deposit for a long time by using a lot of volume of sample. Our case, we can't do that. Our sample volume has to be fixed, or else we can't follow Faraday's law. So we can't improve our signal by increasing the volume. Well, in fact, one of the things that Kelsey is doing right now is, in fact, increasing the volume by small degrees. So instead of a 100 micron thick cell, she's making thicker ones. So if you double the volume, that should double your signal and should get you from 50 to 25 ppbs. The problem with that is that you double the volume, you're increasing the thickness of the cell, which means you have to wait longer to deposit, to exhaust the entire cell. And it's a losing game. You double the thickness, that doubles the signal, but it increases the diffusion time by 4. So there's a limit to how much you can get by going that direction. A smarter way to do this, and this is also Mohammed Maray's idea, is to reduce the noise. Well, what's causing the noise? It's that charging curve that I talked about. Well, charging curve is the charge that has to flow to charge up your electrode surface to the new potential. The bigger the electrode is, the greater its area, surface area, the more charge hits a bigger capacitor, so the more charge has to flow. So we want to make the electrode area smaller. How do you do that? Well, again, the problem is that background that you get is too big. As our signal gets smaller, it's getting closer and closer to that. And when our signal is going to be close to 1.5 microcoulombs, we're not going to be able to measure it very well. So, again, that's that crescent for the 0 arsenic. And if you look closely, you can see it's not 0. That's the 1.5 microcoulombs. We want to diminish that by decreasing the electrode area. So now it's an engineering problem again. So instead of having one big macro electrode, like I've been talking about, we can go over to the clean room and make an electrode array. And these are 3 samples. The shiny part there is the gold, the unexposed gold. We simply create an electrode surface that where the only, most of it's covered up, but the only active areas are those circles. That decreases the physical area of the electrode. Now, we have to keep those exposed areas of the electrodes close enough. This cell is about 100 microns thick, so we want to keep those guys within 100 microns of one another so that the diffusion time to exhaust the whole cell doesn't increase much. So it's hard to see from this slide because the scales are constantly changing. That's the data I showed for you for those other arsenic concentrations. If we skip over to the smallest array, we're just using 5 micron holes. Now we're looking at sub 10 ppb signals. And we can, these are small, but we can still see them and measure them quite well. I should have said the quality of these data is really quite surprisingly high. Any one of these traces here is 3 superimposed runs right on top of one another. So in the short term, it's very, very reproducible. So you can see by going to the array, what we've done is make the 0 or the blank signal smaller, which allows us to look at smaller and smaller charges due to our analyte. We just blow up that 5 micron array system. You can see it more closely. The blank still exists. It's quite a bit smaller than it was before. But you can see that we can now confidently look at much lower concentrations. now we're in the range we really need to be. Now, if you think about concentration levels, what we're proposing here is not a substitute for taking a sample and bringing it back to the lab and doing really high quality analysis. What we're talking about here is a monitoring, an early warning system. So I'm not sure the data here, I'm not expecting the quality of our data to be the same level, be able to get as low a detection limit as you can do in a fancy lab with a fancy technician. But sub 10 ppbs is certainly adequate for an arsenic warning system. If we look at calibration curves generated by those experiments, this calibration curve A is the one for the macro electrode. For the, this is the 50 micron array. You can see that it's the same line. This is just, we can go to lower concentrations now. So this micro electrode array does seem to work quite well. It's really an intelligent way to improve your analysis. And that also is another thing that Kelsey's working on right now. Just about it. So what I've talked about, I think we've done enough work that we're at the proof of concept and beyond the proof of concept level for does the coulometry approach work as a calibration-free, a viable analytical method. I think that's quite clear. We've done enough work that we're getting down to excellent sensitivities. Now there's still lots of other issues. Can we make these guys cheap enough? What kind of sample treatment are you going to have to do when you get a real sample? How long will they actually last in the field? Those are still questions that we have to determine. Then we also have to worry about how do we get power to them and other things. How selective are they? But again, a lot of this stuff I said is engineering. Just to show you a little bit of insight in the engineering, about a little more than a year ago, we got called by some people at Dow Chemical. Dow's headquarters is in central Michigan. We went back to those pollution maps. You'd see a lot of Superfund sites in Michigan. Dow has been a bad guy over the years. But we were called by one of their analytical chemists who said, I'm getting tired of sending my guy out to the field. It's expensive, it's slow, and it doesn't really give me the information I want. Can you guys help me out? So Tommy and his guys slapped together that prototype instrument. You can see my cell, my sensor right in there. He has these big pumps and a control system and so forth. And so a year ago, Tommy got that running for these guys from Dow. And they liked it enough that they wanted to try it out. Unfortunately, a while later, Dow merged with DuPont, and all the projects in both of those companies are on hold until they get the merger straightened out. But this is now, let's see. Tommy's improved the system now. Instead of the big pumps, he now has found these micro pumps that we can use. And so now the system is being miniaturized a lot more than it was previously. What that last slide has is a video of the thing actually pumping. And all talks now have to have videos, but I don't know how to back up. I think I can. Oh, there we are. So I think you might see what the blue is the sample solution going in. If I actually have turned the thing on, you'll see the blue solution get pumped out. So we're using some of his mini pumps. It's not too exciting anyway, so I wouldn't worry about that. I'm sure that we can get that working if we need to. But basically, we built in some valves that are built into the chip, and we have the mini pumps here that are pushing the sample solution through. But if anybody's interested in this, we'll work on it. We'll work on it after you get some pizza in your front of you. But basically, that's where the project is now. We still have a lot of work, both chemical and engineering, to do. We now have a platform that we think is viable. But we have a lot of chemistry to do to extend this from arsenic solutions in our bench to arsenic solutions that are real, that have other components in, that might need some pre-treatment and so forth. And then there's still a lot of engineering work to actually take this device and get it so that we can put it on the sidewalk and do a trial where we're turning the thing on and off and making daily inquiries a few times a day at our leisure rather than just when we send it to get a snapshot. So that's where the project is now. I think sort of a perspective over the years, when I started here in the 70s, the speed school was a very different place. You can't believe how different it was, both building-wise, professor-wise, and mentality-wise. Back then, sciences disciplines didn't cooperate very much. I stayed in my lab and did my thing. Now, the most exciting projects are almost always interdisciplinary. So the ability for physical scientists to cooperate with engineers has opened things up much more than they were before. So with that plug for both the speed school and the chemistry department, I'll shut up. If you have any questions, I'll try to answer them.